Okay. So, tangent of A plus B. As I was saying, sine of A plus B over cosine of A plus B. And we can do that because we know tangent is sine over cosine, right? That's old news. Now, the advantage of doing this is sine of A plus B. Can we use one of our sum and difference identities above to rewrite sine of A plus B? Yeah. So, we're using sine of A plus B, we're using what? Sine of S plus T. So this rewrites as what? Sine A cosine B. It's a sine, so I'm going to keep it plus. And then it becomes cosine A sine B. Denominator. Same process, but with the cosine. So now, cosine A plus B, so it's cosine, cosine. So cosine A, cosine B, opposite sign, so now minus, sine A, sine B. Okay, we good there? Now, this next part is a part that I wouldn't expect you to remember because we kind of are at a stuck point and you kind of have to know the next step to go. I don't know if you remember anything about what the tangent sum identity looks like. It's a fraction. And obviously we have a fraction here, right? And if you recall, or don't recall, that's fine, the first entry in the denominator is a 1. So right here, where I currently have cosine A, cosine B, that needs to become a 1. How do you turn a cosine A, cosine B into a 1? Divide by cosine A, cosine B. If you divide that part of this fraction by cosine A, cosine B, you need to divide everything by cosine A, cosine B. Okay? So, it's going to get kind of messy, but we're going to take, so there's 4 pieces, if you would. I'm going to divide each of those by cosine A plus B, or cosine A, cosine B, sorry. So, I'm going to do sine A, cosine B. I'll change colors here, and I'm dividing by cosine A, cosine B. Plus, the other part I have in my numerator is cosine A, sine B. And we're going to divide it by that same cosine A, cosine B. Okay, big fraction bar. We're going to do the same thing with the denominator pieces. So it's cosine A, cosine B. And we're going to divide cosine A, cosine B by cosine A, cosine B. And this time it's minus, and again, sine A, sine B. And we're dividing by cosine A, cosine B. Kind of running out of room here on my right side. Okay. All we have to do is do the appropriate cleanup, simplifying, and we're going to be at our final answer. So, look at each piece. What about sine A cosine B divided by cosine A cosine B? Yep. Cosine B's cancel. What is sine A over cosine A? Tangent A. Okay, plus. Clean up the second fraction. Cosine A sine B divided by cosine A cosine B. Cosine A's will cancel. What's sine B over cosine B? Tangent B. I'm going to wipe this out and move it over a little bit. So your numerator is tangent A plus Tangent B. Denominator. What's cosine? What happens with cosine A, B, cosine B divided by cosine A, cosine B? They all cancel. What remains? 1. Minus. Okay. Anything cancel in the next one? No, nothing cancels, but it's sine A over cosine A and sine B over cosine B, which can be rewritten as what? Tangent A, tangent B. So in my denominator, I'm now going to have 1 minus tangent A, tangent B. Maybe vaguely familiar, that fraction? Okay, that was the sum identity for tangent. Now, I'm going to write a couple of side notes over here that the first entry in the denominator equals 1. And so because the first entry in the denominator equals 1, that was why I decided to divide by cosine A, cosine B. Make sense?
But when they don't just give us, like up on the formulas at the top, don't include the tan formulas from last year.
I don't know why they don't include, why they just include the sine and cosines up there. Honestly, I would say be familiar with the tangents as well. Now, in all honesty, do we use the tangents as much? No. We focus more, we use the cosine and sines more. The developing, again, that's just, it's a good skill to have to be able to figure out what you need, but if you know it, that's even better. Now, if you guys don't mind, I wasn't going to necessarily go through all of 4. What's 4 doing? Develop the identity for tangent A minus B. So what's the difference? We have, our signs basically change, right? So you would set it up the same way. Like if we were going to go through it, you would start off the same way in that tangent of A minus B, well, we know tangent would go to what? Sine over cosine. I put the wrong symbol in there. So remember, tangent would be sine over cosine. We could set up our sum and difference identities there, right? Here's what I want to do. Based on what our answer was last time, do you remember what the identity for tangent of A minus B looks like? What changes? Yeah, our plus minus signs change, right? So since this starts off tangent A minus B, well, that plus on top changes to minus, the minus on top changes to plus. So this would equal, if we actually worked it out, which, sorry, I'm taking the lazy route out, tangent A minus tangent B over, instead of 1 minus, it's going to be 1 plus tangent A, tangent B. Okay, the steps would be very similar, almost identical to what you had earlier, except the signs are different. So I hope you can handle me skipping over that. Questions there? Okay. Of the identities, we probably covered the ones that to me were more interesting and easier to use. But we're going to talk about a couple other sets of identities today. Double angle identities are listed below. the double angle identities, there was 1 for sine. So sine of 2x is 2 sine x cosine x. And then if you recall, there were 3 for cosine 2x. They're all equivalent in a way, based on our Pythagorean identities. But, so cosine 2x is 1 minus 2 sine squared x. Or cosine 2x is 2 cosine squared x minus 1. Or cosine 2x is cosine squared x minus sine squared x. Those are all equivalent. Okay, again, do those randomly pop up in our calculus? They do. Regular basis, not so much, but kind of a random pop-up stuff. Okay, on the back it says we get them by doing the following. And so I'm going to try and take you through a quick develop on each of them. So if we start with the sine 2x. Okay, sine 2x. Think about our original 6 identities. 2x is what plus what? X plus x, I think I heard in my ear. I say that just because there's kids in the hallway right now, so. The reason I didn't close the door when the bell rang, because I knew you'd be back for your phone. Okay, so sine of 2x can be rewritten as sine of x plus x, because 2x is 1x plus 1x, right? Now, think about our identity, our sum of sine identity. Sine of x plus x, rewrite it based on the front side, so sine cosine plus cosine sine. So it's going to be sine of x, cosine x, keep it as plus, and then you flip these, cosine x, sine x. Okay. Clean this up. What is sine x cosine x plus cosine x sine x? 2 sine x cosine x. Because aren't these like terms? Even though the pieces are flipped, they're like terms. So sine x cosine x plus sine x cosine x is going to be 2 sine x cosine x. So right there, we have just proven that one, or developed it, that sine 2x is 2 sine x cosine x. Okay? Now, let's attempt to do the same type thing with cosine. Except cosine, we need to come up with 3 answers, so we'll have to keep adjusting. But cosine 2x, you can guess the first step, right? 2x can be rewritten as x plus x. This is cosine of x plus x. If we go with our sum of cosine identity, this is rewritten as cosine cosine. So cosine x cosine x. Change the middle. So now instead of plus, it's going to be minus. And then it's sine x sine x. Clean that up. What's cosine x cosine x? Cosine squared x minus, what's sine x sine x? Sine squared x. And notice right there, isn't that one of our 3 identities? That cosine 2x equals cosine squared x minus sine squared x? Okay? Now, to get the other 2, take what we have here and let's make an adjustment. One of our other 6 key trig identities can be substituted in here and help us out. Thoughts? Okay, Pythagorean identity, right? Sine squared x plus cosine squared x equals 1. So pick one of these. It doesn't really matter which. So if I pick cosine squared x right now, what is cosine squared x equivalent to using our Pythagorean identity? That is equivalent to 1 minus sine squared x, true? And then we already have another minus sine squared x here. So if I take that cosine squared x, use my equivalent statement for my Pythagorean identity, and now have 1 sine squared x minus sine squared x. Well, clean that up. We have 1, it's minus sine squared x minus sine squared x. It's going to be negative 1 minus 1 makes it minus 2 sine squared x. So I now have 1 minus 2 sine squared x. Guess what? That's another one of my double angle identities. Okay? Now, my recommendation to get the third is to go back to our previous one. If we go back to that cosine squared x minus sine squared x, this time instead of replacing cosine squared x, replace sine squared x. So it's still going to be cosine squared x minus, what can sine squared x be replaced with in terms of Pythagorean identity? One minus cosine squared x. Clean that up. I have cosine squared x minus negative cosine squared x, which makes this 2 cosine squared x minus 1. So that is your third one there. Okay? Again, best to just know those, but also trying to get you guys to look at connections. They all connect, that kind of stuff. Okay, do you remember the double angle identity for tangent? I don't usually either, so let's take a similar process here and go through this. Tangent 2a. Well, what do we know about 2a? It's a plus a. So this is tangent of a plus a. Didn't we just write this formula on the front? It's a fraction, right? On top, it was stated as tangent A plus tangent B. So in this case, our A and B, though, are both A. So this is tangent A plus tangent A. And then it's 1 minus tangent A, tangent B, which in this case, again, they're both A. So 1 minus tangent A, tangent A. Is the fly bothering you guys back there too? Because I have a fly that keeps bothering me up here too. Okay. What's tangent A plus tangent A? 2 tangent A. 1 minus tangent A times tangent A. 1 minus tangent squared A. And this is your double angle identity for tangents. Okay. I would be happy if we can get through half angle identities there. If we leave the log stuff for tomorrow, fine, so be it. But if we can get through all this half angle stuff, that'd be good. Okay, half angle identities. There are a couple of different ways to write these, but what they have written right here, sine of theta over 2, excuse me, is plus or minus the square root of 1 minus cosine theta over 2. Cosine of theta over 2 is plus or minus 1 plus cosine of theta over 2. With these, remember you decide the plus or minus based on what quadrant you end up in. Okay? So, now, notice it says the double angle identities can be manipulated as follows to find the half angle identities. So, I'm going to attempt to show you the connection there. So let's start off with the cosine double angle identity. Let's see. We're going to use the one that uses sine right now. So I'm going to start off with cosine of 2x equals 1 minus 2 sine squared x. So that's one of our double angle identities from above, correct? Or from previous page, if you prefer to think of it that way. Okay. And by manipulating this, what we're going to be working towards is, I'm working towards this first one here, the sine of theta over 2. Which means the first thing I'm going to ask you to do is work to isolate the sign, as in the SIN sign. So if we're working to isolate the sign, how do you guys feel if I say let's add the 2 sine squared x over and subtract the cosine 2x over to the other side? Just getting a positive there. So if I add 2 sine squared x to the left, 2 sine squared x equals, on the right, I still have a 1. And I'm going to subtract this cosine 2x over, so minus cosine 2x. Is sine squared x by itself? Not yet. We need to divide by 2. So we divide by 2. I now have sine squared x equals, and in my notes it looks like for right now I just do one big fraction. So 1 minus cosine of 2x over 2. Now, the part we're trying to get here is we're trying to get sine of theta over 2. I currently have sine squared of x. And, even if we just work in a different variable, we need this to be divided by 2. Here's the trick we're going to use. Every place I see an x in this expression, I'm going to replace the x with theta over 2. Okay? And by doing this, we'll be able to get to our half angle identity with a little bit more work. So, if I take that x, every place I see x, I replace it with theta over 2. That means sine squared x now becomes what? Okay, good. Sine squared of theta over 2. 1 minus cosine of 2x is now going to be cosine of 2 times theta over 2 all over 2. You see some cleanup there? So I'm going to leave it as sine squared theta over 2 for right now. If you clean up the right, it's 1 minus cosine of what? What's 2 times theta over 2? Just theta all over 2. Notice I'm almost there. I have sine squared theta over 2. I'm trying to get to where I have sine of theta over 2. What's the step I do? Take the square root. If we take the square root of the left, we take the square root of the right. The square root of sine squared theta over 2 is just sine of theta over 2. Anytime you take the square root in an equation setting, we're going to say plus or minus the square root of 1 minus cosine theta over 2. And again, the point of that is to show the connection between double and half angle identities. What? I have a feeling there's more than one fly, because I feel like at that same time I had a fly up here that you're trying to... Okay, now, to do the other one. That time we used cosine 2x and sine squared x. This time we still want to use cosine 2x, but we're going to use the cosine squared x. So I'm going to start off with cosine of 2x equals 2 cosine squared x minus 1. Same job. Work to solve. That's what I'm looking for. Solve for cosine x. So if I'm going to work to solve for cosine x, can we say add 1 to the other side? If you don't mind, I'm going to flip my sides as I go as well. So I'm going to put my 2 cosine squared x on the left. And then I'm going to have cosine 2x plus 1 on the right. Is my cosine x by itself yet? No, we need to divide by 2. So now cosine squared x is going to be cosine of 2x plus 1 all over 2. What's the step that I did at this point last time? Okay, we're going to replace x with theta over 2. So cosine squared of x is cosine squared of theta over 2. Cosine of 2x is cosine of 2 times theta over 2. Still plus 1, all divided by 2. Clean up. Still cosine squared of theta over 2 for the moment. Cosine of 2 times theta over 2 becomes cosine of theta plus 1, all divided by 2. And final step is to square root. Cosine of theta over 2 equals plus or minus the square root of cosine theta plus 1 all over 2. And I kind of ran out of room there. It's supposed to look something like that. Okay. Last identity example. Show that sine of x divided by sine 2x is equal to secant of x over 2. For all value of x that makes sense. When it says show, I'm going to use the idea of prove. So we want to prove that the left side equals the right side. Which means I'm going to start with the left side, sine x over sine 2x, and we're going to work to manipulate it until we end up with that right side. So my goal at the end is to have secant x over 2. My question right now is, okay, what can I do to head that way? Anything we can replace? You got it. Sine of 2x is the one we're replacing. So sine x stays on top. I'm just going to carry that over. According to our double angle identity, sine of 2x is equivalent to 2 sine x cosine x. If you can get that first step, I personally think it's an easy problem once you see that first step. What do you see that can happen here? Sine x can cancel with sine x. What remains on top? A 1. What remains on bottom? 2 cosine x. And what do you know? Okay, yeah. Cosine x is a reciprocal of secant x. And so cosine x can move to the top and become secant x. What about the 2? It stays. And so now we have just shown that sine x over sine 2x is equal to secant x over 2. I'm going to stop there on notes today because that's a good stopping point. I can't, there's no way I can get through all of those graphs of logs in the next 9 minutes, okay, and do a decent job. So I'm going to hold those for tomorrow. We can use this last bit of time to do some 11 checking if you want. And then tomorrow, there's no way that those graphs will take me the entire period at all. So, because we'll just, practice our left, right, middles, our graphs, and then go from there. Okay?